In this video, we'll be covering a weak acid titration. The concepts are so similar. So this is weak acid titrated by a strong base. And the concepts are so similar that we probably won't, we'll probably just cover strong base and strong acid titration. And then there's actually three titrations. There's weak acid and a strong base. Then you could have a weak base and strong acid titration, and then a strong acid, strong base titration. The concepts are so similar that I just chose one of these to cover by video, and the other ones we'll just do, as like practice problems in class. So let's go ahead and get started on a couple of terms. So a titrant is the stuff in the burette. So that would be like here with the switch. Okay, and then as you add it over time slowly, then the volume actually decreases in here. But the way you read it is by total volume in here, and you don't care about where you start or where you end. All you care about is where the total amount, like the change in volume that got added. So in this case, we're doing a weak acid titrated by a strong base. This is a strong base that would be in the burette, so this would be OH or specifically NaOH, but as we know, the Na is a spectator. The titrate or analyte is the solution that's in the flask that's being it's being analyzed. So this is the one that usually usually we don't know the concentration. All we know is the volume that's in here because we would have measured the volume. And we may not even know the acid, the identity of the acid. So you could use titration to figure out the identity of an acid. So based on its, you could figure out the pKa based on what pH you're at, and then you could figure out what the unknown acid might be just based on a titration curve. So we're going to go through step by step through a problem, a weak acid titrated by a strong base, and kind of take a look at all the different points during a titration. So usually your setup looks like this. You'll have a pH meter, and the display looks like that. And then you have, so this is in our flask. And then you have a burette that's adding OH. Okay. And sometimes depending on your setup, sometimes it'll be on a stir plate. Okay, and you'll have like a stir bar in there, and it's swirling the whole time that you're adding. And then you're recording pH after, let's say, like zero point 0.2 or actually a full milliliter of OH. So this would be volume of OH. Typically, it's in milliliters. And then on your y-axis, you'll have pH. And this titration will look like this. It's going to show a curve, something like that. Your pH during a weak acid strong base titration should be a little bit basic depending on the weak acid. So here's pH of 7 would be like here. This would be 0. This would be 14 up here. And we're going to look at different points in this tutorial. So we'll look at point A when no base has been added yet. Then we'll look at point B, point C, and point D. So this is point E. So point A, no base has been added yet. No base added yet. Points B, C, and D. These are all the buffer region, or I like to call it the buffer region, because the only species present are going to be the weak acid and its conjugate. Okay, so you could use the Henderson-Hasselbalch equation, and we're going to summarize all of this on a. I have like a whole form to fill out that has the various different titrations. So we could use the Henderson-Hasselbalch equation for titrations that are in this region. For point E, this is called the equivalence point or endpoint. It's called the endpoint when you're referring to an indicator, but the technical name is the stoichiometric point, and or the equivalence point. So it has like a couple different names. Equivalence point. And any point after that are overshoot points. So this will be point F. So in this tutorial, we're going to do a problem for A, B, C, D, E, and F, and then see how they compare and contrast, like how these problems are done. On this F point, so this is the overshoot. And this is where this depends only on the amount of OH. So you can ignore any, you'll have just the conjugate in OH, but since OH is strong, you could ignore the conjugate. All right, so let's go ahead and get started on this. So point A, no base has been added. So acetic acid is our weak acid, and we'll call that HA just to keep it simple, to keep things simple. So there's no chemical reaction here because you haven't added base yet. So this is really just a simple equilibrium problem that we did already a month and a half ago. So so no base is added. We ice it up. So our initial amount, if we go back to the original description of the problem, our initial amount was 0.200 molar, and so minus x plus x plus x. So we have x squared over 0.200 minus x. The assumption rule should be perfectly fine here. So x equals the concentration of H plus, and we get 1.9 times 10 to the negative third if we solve this out. So taking the negative log of that number, then we get 2.72 for our pH. Okay, so that's point A. You use an ice table on point A. Okay, point B, some base has been added. So now our species present is we have a weak acid. So this is a weak acid, and now we have OH or NaOH, so we have OH minus, so we have a strong base. So we have a weak acid and strong base. So here we have to do an earth table. And remember with earth tables during titrations, you're always working with almost always working with milliliters during a titration. So use millimoles. It's so much easier. And I know you guys might not be used to it, and you want to be technical and you want to be right. It is right. It's right to use millimoles because we'll be dividing by milliliters later, and it's way more work to convert it twice. So why convert it at all? So a millimole is when you take a milliliter and you times it by the molarity, and then that gives you a millimole, which is way easier to work with because then if you divide a millimole by a milliliter, then you get back to molarity, which is sometimes useful. So we need to figure out how much weak acid we had. So this will be 100 times 0.200. So this is 20.0 millimole of weak acid. And next we need to figure out how much weak base or strong base, sorry, that we had. So OH is we're gonna add 50 milliliters of zero point 0.1 molar. So 50 milliliters times 0.1 molar, and this gives us 5.00 millimoles of OH minus. And so we're in the buffer. We're gonna end up in the buffer region. I'll show you how this works. So we have HA plus OH minus, and this is going to create the conjugate, and water will be the other product. So this is a full-blown chemical reaction. So that's why we're working with moles and using earth table and we had 5 of this there's 0 and water doesn't matter. So minus 5.00, this is way in excess, the weak acid, 1 to 1 here, and this would be plus 5.00. So our weak acid amount goes down to 15.0 millimole. This is 0, and then this is 5.00 millimole. So now notice that we have a weak acid and its conjugate. There are no other species present, so we have a buffer right now. And when we have buffers, we can use the Henderson-Hasselbalch equation. So pH equals, and we have the pKa is 4.74 plus the log of base over acid. So we have to put this over this number. So 5.00 divided by 15.0. And so we have a pH of 4.26. Okay, so that's the key part of this problem is we're in the buffer region. We consumed all of the strong acid that was added, so there's none left over. And so we ended up with forming some of the conjugate, and then we have HA remaining. So we could use the Henderson-Hasselbalch equation to do this part. Okay, so on to point C. So now we have 100 milliliters of 0.1 molar OH, and this is from the previous, from part B. Our HA millimole, our amount of HA was 20.0 millimole of HA, and for OH we have 100 times 0.1, so we have 10 millimole of OH. So you'll see an interesting thing happens here. You're gonna get half of this consumed if you think about an earth table in your head right now. So we have HA plus OH, and you're gonna get A minus H2O. So this is 20, this is 10, this is 0. This doesn't matter. So minus 10, and then we have 10 left over. This gets fully consumed, and this goes up by 10. So we have 10 and 10. We have a 1-to-1 ratio now of the conjugate pair. So at point C, we are at what's called the halfway point. So the pH is the pKa 4.74 plus the log of 10 over 10. So this part right here is 0. So pH equals pKa, which equals 4.74. And this has a special name. This is called the halfway point. So at the halfway point, this is true. The moles of acid equal, or actually the moles of strong base equal half of the moles of weak acid. This statement is also true. The moles of weak acid end up equaling, when this is all said and done, after you put it through the earth table, these two are also equal. So the moles of are equal. So the moles of weak acid equal the mole of the conjugate base at this point. So that's the halfway point. Okay, moving on, we're now at point D. This should be another, so we had 20 millimole of weak acid, and then we have 15 millimole of strong base. So let's run this through the earth table. So this is 20.0, 15.0, again, all of the base gets consumed. At this point, we start to have a little bit more conjugate base than we do the acid. So this goes down to 5. This gets fully consumed. This is all the way up to 15 now, the conjugate. But again, we're at another buffer point. So again, we could use nothing too new here. We could use the Henderson-Hasselbalch again at this point. So now we have the log of 15.0 over 5.0. So if we calculate this out, uh, it goes up past the pKa, so now it's greater because we have more base present than acid. So our amount actually is greater than the pKa, so it's going to go up to 5.22. So that's the pH at this point. Next is point E. This is the equivalence point. So we have 20 millimoles of strong base now, and we had 20 millimoles of weak acid. So here's what happens. So we have A minus plus H2O. So these actually go to completion, and the only species present when this happens, so this is the only thing this is the only species present. And so there's no further interaction, and notice that we don't have a buffer anymore. Okay, so all we have is a conjugate. So what this will go on to do is an ice table. So at the equivalence point, this is what this is called. This is called the equivalent point or stoichiometric point. And so what we have is we have to first deal with our earth table, and then now we need to do an ice table with the conjugate. An important thing to remember now is that we were in millimoles here. This is millimoles. And we need to make sure we account for the new total volume, because the volume has been changing this whole time because we're actively adding more and more volume of base, which is going to add more total volume to the flask, to the titrant. So let's deal with that on the next slide. So if we remember back to our from the F line on the earth table, then our amount of conjugate base was 20.0 millimoles. And we need to remember on ice tables where we need to be working with volume here. So our total volume, we need to divide this by our new total volume. Let's use a different color to emphasize. So we want our total volume, and during titrations the volume is constantly changing because you're adding more and more base or titrant, whatever's in there. So originally we had 100.0 of the weak acid, so that volume counts, and then it took 200 to get to the equivalence point, so we need to add all of that. So that's how much base we added. Okay, so we need to add both of those, and then we would get 300 milliliters. And so on our ice table, we need to make sure that we use molarity. So this would be, if we calculate this, 0.0667 molar. So I'll need to write our other reactant down here. Actually, let me write this here. Our other reactant is water, because this is a base reaction. Since that's what we have only the conjugate base. Okay, so water, just put dashes there. This is 0. Remember, so we did have some initially, but this is post reaction. So this is post earth table. So now we have none because they were fully consumed, and then we also have none of that. So this is after like all this action happens when you add the strong base to the weak acid. All this action happens, And when all the dust has settled, what is left? This is what's left. 0 of that and 0 of that. So then it goes on, and then you have tons of this. So that it goes on to act like a weak base. So it just turns into a weak base problem um, when you're at the equivalence point. So this would be minus x, and plus x. And so this is 0.0667 minus x, and x. And so here's another little nuance about doing the equivalence point is this is a base. So this is a base now. So we need to be using KB. So we need to convert um, uh, our KA into KB. So our KB is 5.6 times 10 to the negative 10th. So, and I'll make a little note of that so that if you ever review this later, like a week or 2 weeks from now, you'll remember, or if you check your notes, to remember to do this. So this is KB, which is equal to KW over the KA of HF. Okay, so there's a couple little things. You gotta make sure this is in molarity, and so you have to account for the total volume, and you need to convert to KB. So if we solve for x here, then we get that OH is 6.1 times 10 to the negative 6 molar. And so our pH would be equal to 14 minus the POH. So 14 minus the negative log of 6.1 times 10 to the negative 6. So we get a pH of 8.79. Okay, and one thing to note here, they like to ask this question on the AP exam. They like to ask this specific question. They like to ask, why is the pH greater? Why is it not neutral? So why is the pH? Why is it not neutral? Okay, and then they'll give you a list of possible responses, and they'll say because OH is being added. Okay, this is incorrect, and they're going to try to make you think that you go, oh, it's OH is added, so you have a basic pH. This is incorrect. You're ignoring what just happened if you like circle this answer. Usually, this is a multiple choice question I've seen on past AP exams. So what I mean is you're ignoring what happened is the OH became 0. Okay, the OH became 0, so it's not from adding the OH. They fully consumed each other. The reason it's not 7 is because you created the conjugate base. That's why it's not 7. Okay, and then the conjugate base goes and does equilibrium with water. Okay, so it's not, so the pH is greater than 7 because the conjugate base of the weak acid does what it does what all conjugate bases of weak acids do. They do equilibrium with water and create a small amount of OH, which is exactly what happened. So you created a little bit of that. Okay, and it's you shifted this to being not neutral. So neutral would be 1 to the negative 7th. So you shifted it to be greater than that. All right, so we have one more point to analyze during the titration, and this is an overshoot point. So this is a overshoot. And here is where your moles of strong base have overcome your moles of HA. So this is going to be your limiting reactant in your earth table. So if we have 250 milliliters of strong base, that would be 25.0 millimole of strong base, and our weak acid never change, so that's 20. So our reaction will be this. Okay, so this is 20, 25. This is 0. This doesn't really matter. Okay, so now this is our limiting. So we subtract 20 here and 20 here. So now we have excess, or sorry, it's 5. We have excess OH, and this is 0. Okay, and this we have a lot of, but it's not going to matter. So even though you have 20 millimole of the conjugate, you have strong base is in excess now. So this is in excess. So the pH is determined. So basically, so really you have a strong base and a weak base. And when that happens, usually the pH is, unless this is some really, really insanely high number, and the KB is really, really high, then you might have to factor that in. But I've never seen that on titration. So this is pH is controlled by this only. So we can ignore this because you have a weak and a strong. So we ignore the weak when you have a weak and a strong. So pH is controlled by OH only. Okay, one little nuance though about this though is remember that we don't just take the negative log of that. Remember these are millimoles, so we need the concentration of OH. So that would be 5.0 millimole divided by our total volume. So we had 250. So we had 250 from the OH and then 100 from the original weak acid that was in there. So that's going to be 5 divided by 350. So our pH would be 14 minus the POH, which equals 14 minus the negative log of 5.0 over 300. Okay, so if we type this in our calculator, we get 12.15 for the pH. And notice this is like way higher than the previous point. So we had 8.79 and just a little bit of overshoot. So just what was it? Yeah, 50 extra milliliters. That's actually a lot actually in a titration, but you see that it spiked way up compared to like the buffer points that we calculated, or all the other points for that matter. So here on the overshoot point, we just did the equivalence point in part E. So that was part E. In part F, we're like way up here. So notice that there's like a huge jump here on the y-axis. Okay, for the pH. Okay, we'll go ahead and we're gonna match what happened, and we're gonna analyze this a little bit further, so we can create we'll match it up with the titration curve. I kind of did this and I mentioned it here and there in the video, but we have a worksheet that we'll fill out. I'll either make another tutorial or we'll handle it in class. But for now, that's the end of our tutorial on titrations.